Okay, welcome to the third installment on the lecture on section 3.4. We are still working in section 3.4 here. What we had done last time is we had found a complex solution to a differential system, a linear system like this, y prime equals a times y, but where a was a real valued matrix. So we had found ourselves a complex solution, and I had stated that the real and the imaginary parts would be real solutions. Whoops. Okay. So that's what we're going to prove. Okay. So given a system like this, well, I'm going to refer to that differential equation as star. Okay. We're going to prove if y, which is the real part plus I times the imaginary part, is a complex solution, then the real part and the imaginary part are real solutions. Remember, the imaginary part is a real valued function. It's the real valued function that gets scaled by an imaginary scalar of I. Okay. So we always, to prove an if-then, we suppose the if. So suppose that y, which is the real part, plus I times the imaginary part, is a complex solution to star. And what it means to be a solution is that then I know that d by dt of y, which is the real part, plus I times the imaginary part, is equal to a times the real part plus I times the imaginary part. Okay, now this equation is not what I am trying to prove. I know that is true. That is just spelling out what my supposition means. So I don't need to work with just one side of this equation at a time. That equal sign is justified. That's exactly what we supposed. So all I'm going to do is simplify both sides. Okay. So I'm going to say that this is the derivative of the real part plus the derivative of I times the imaginary part. That's just the sum rule for derivatives. Similarly, over here, I'm going to use the fact that matrix multiplication distributes over vector addition. So this is a times the real part of y plus a times I times the imaginary part of y. Now, what I'm going to do on the left and right side is fairly similar. I'm going to pull that scalar of I out. Over here on this side, I'm using the constant multiple rule for derivatives. So I'm going to say this is the derivative of the real part plus I times the derivative of the imaginary part. That's the constant multiple rule for derivatives. Over here on the right, I'm also going to pull out the I, but that's the fact that scalars pull through matrix multiplication. So I'm going to have a times the real part plus I, a times the imaginary part. So, this is fantastic. I have simplified both sides. Notice both sides now are a real valued function plus I times another real valued function. Or, yeah, a real valued function plus I times another real valued function. The imaginary part is a real valued function, so its derivative is real valued. And when I multiply a real valued function by a, it's still real valued. Because I started with real valued functions here, taking the derivative and multiplying by a also preserved that they were real valued. Okay. So I've got my left-hand side, which I know is equal to my right-hand side. But when we're working in the complex system, two complex expressions can be equal if and only if the real parts are the same and the imaginary parts are the same. So the real parts are equal. That means the derivative of the real part, because that's the real part of the left-hand side here, must equal a times the real part of y, because that's the real part on the right-hand side. But what does this equation say? That says that the real part of y is a solution to my differential equation star. That's exactly what that means. And now I just have to do the same thing for the imaginary parts. The imaginary parts are equal. So, the derivative of the imaginary part is equal to a times the imaginary part. There, I was also just taking the imaginary parts of each side, remembering that the imaginary part does not include the I. Okay. But what does this say? This tells me that the imaginary part of y is a solution 2 star, which is exactly what we wanted. So now we know if we can find one complex solution, there are 2 corresponding real solutions, the real and the imaginary parts. Those will give us our 2 independent solutions. Now I have not proved that they are independent. You'll be doing that in the homework. I think it's question 19, but I don't remember. I looked that up before I shot the video the first time, and I had cut off the bottom row, so this is take 2, and I don't want to go look it up again. Anyway, that's what we have. You'll be proving that they're independent in the homework, but that gives us everything we need. Yay!